Now let's discuss limits quote unquote at infinity, or looking at what happens to a function in the long run. Here, the role of infinity is the opposite of its role for vertical asymptotes. Now we will be finding the limit as x approaches infinity, or negative infinity, and seeing what happens to the y values. If the y values level off to something or approach a limiting value, we would say that the limit of f of x as x approaches infinity is that value. This value could be different if x is approaching infinity versus negative infinity, so here I'm just using L1 and L2 to denote the value of the limit. These are what we call limits at infinity. And if we get a finite number out here for the limit as x approaches positive or negative infinity, then the horizontal lines y equals L1 and y equals L2 are horizontal asymptotes of the graph of the function. Not all functions have horizontal asymptotes, but those that do could have one or two horizontal asymptotes. We can't have any more because we're only looking as x approaches infinity way out in this direction, or negative infinity way out on the graph in this direction. There's no other way to approach infinity or negative infinity, there's just those two options. Here's an example of a function that has zero horizontal asymptotes. This is the graph of f of x equals x to the third. This function does not level off as x approaches infinity, it just keeps on growing. It also doesn't level off as x approaches negative infinity, it just keeps on going down. This graph shows an example of a function that has one horizontal asymptote. It is shown in the graph labeled as y equals L. We can see here that the y values as x approaches infinity out in this direction are coming down towards this value. Whatever that is what we're calling L, and we would draw the horizontal asymptote as a dashed line. Note that this is still a horizontal asymptote, even though as x approaches negative infinity doesn't have the same result. This function seems to just keep on going down. In fact, it even crosses the horizontal asymptote at one point. That is okay. We can cross a horizontal asymptote. However, we cannot ever cross a vertical asymptote. In fact, there are examples of functions that cross their horizontal asymptote an infinite number of times. If we have a function that oscillates like this, but it's oscillating slower and slower and slower, and it just sort of hovers around this y value, then it will continuously cross it, but it will be approaching a y value. We won't see functions that look like that, but they do exist. The last graph here is showing an example of a function that has two horizontal asymptotes. If we get two different values for the limit as x approaches positive infinity and x approaches negative infinity, then this is how a function can have two horizontal asymptotes. We also won't see functions that look like this. The functions that we'll be looking at are rational functions, which always have the same horizontal asymptote in both directions, if they have one. Let's take a moment to consider a real-life example as a way to understand this concept and also practice with notation. Here we have a graph that shows the temperature in degrees Fahrenheit, which we'll call capital T, of an apple pie, little t seconds after it is removed from an oven and placed on a cooling rack. To be clear, the horizontal axis is little t, which is measuring time in seconds. The vertical axis is capital T, which is measuring temperature in degrees Fahrenheit. The first question says, find the limit as little t approaches 0 from the right of big T. As little t approaches 0 from the right, we will be going along the function and letting little t, the time, kind of go backwards to the beginning. If we go along the function here, we can see that the y values are heading towards this point right here. And I know that it's kind of hard to see what that value is, but this is 400 and this is 440, and then we've got some increments here in tens. This is halfway between 420 and 430, and so this point here is 425. So the limit as time approaches 0 from the right of the temperature is 425 degrees Fahrenheit. This represents the temperature when the pie is removed from the oven, when T equals 0. So, in other words, this is the temperature of the oven. In part B, we'd like to find the limit as little t approaches infinity of big T. So what this is asking is, as time goes on, as time approaches infinity, as the pie just sits on its cooling rack forever, what is happening to the temperature? Well, we can see from the graph that the temperature starts right when it's removed from the oven at 425, and then it rapidly starts cooling, and it begins to approach some value. This should make sense. It's not as if the pie is going to keep on cooling down and down and down forever. Yeah, I know that we only have an hour's worth of information here, but we can already see that the y values are hovering or getting up closer to whatever this y value is here. I know that it's a little hard to see, but this is about 70 degrees. So we can say that the limit as time approaches infinity of the temperature is 70 degrees Fahrenheit. Now what this represents is the room temperature, because the pie won't cool down below whatever the temperature of the room is. Now let's look at some examples with actual functions to work with. Just as with vertical asymptotes, rational functions are ones that normally have horizontal asymptotes too. So let's start with the simplest kind of rational function, which is just 1 over x. Let's see what happens to this function in the long run, or as x approaches positive and negative infinity. We'll start by looking at a numerical table. As x approaches infinity, what that looks like is x just getting larger and larger and larger. Infinity is not a numerical value, it's a symbol that just means larger and larger and larger. So we can just start by plugging in something like 10, 100, 1,000, 10,000, and 100,000. But we can always get bigger and bigger, just as how we can always get smaller and smaller and approach a number when we're finding limits. Pause this video and see if you can determine what the f of x values are for each of these x values. You should find that you get 0.1, 0.01, 0.001, 0.0001, and then 0.00001. So you can see here that the y values are getting smaller and smaller and smaller. In other words, they are approaching 0. We can see that in the graph, even though we only go out to 6 here. As x approaches infinity or gets larger and larger, the graph is approaching the x-axis, and that is a y value of 0. So we would write the limit as x approaches infinity of 1 over x is equal to 0. Because this number that we got out for this limit at infinity is a finite value of 0, then we would say that the horizontal line y equals 0 is a horizontal asymptote of the graph of f of x equals 1 over x. Let's take a look and see what happens in the other direction. We could probably see that from the graph we should also get 0 out. To let x approach negative infinity, we can try to plug in numbers like negative 10, negative 100, negative 1,000, negative 10,000, and negative 100,000. If we plug these x values into the function 1 over x, we will get the exact same values as above, except they'll all be negative. So we'll get negative 0.1, negative 0.01, negative 0.001, negative 0.0001, and lastly negative 0.00001. These are also approaching 0. They are just all negative, but they are getting closer and closer to 0. Again, that makes sense with our graph. The function is below the x-axis, so it will get closer to 0, but with negative numbers. So we would write here that the limit as x approaches negative infinity of 1 over x is also equal to 0. And again, based on these two limits here, we would say that the function f of x equals 1 over x has a horizontal asymptote of y is equal to 0, or the line y equals 0. Of course, we would like to be able to determine these limits for functions that are more complicated than just 1 over x. Well, it turns out that if you have any fixed number in the numerator, and you're dividing by x to a positive power, this will always eventually approach 0 as x approaches positive or negative infinity. So in symbols, what that says is that the limit as x approaches infinity of some number, fixed number, no x's, divided by x to a positive power is 0. Also, the limit as x approaches negative infinity of that same situation is also 0. Let's see graphically why this is true. Well, we just saw that the graph of 1 over x does approach 0 as we let x approach positive and negative infinity. We can actually go really far out, and we can see that it doesn't take long for the function to get closer and closer to the x-axis. If we change the denominator to be squared instead of to the first, then we still have this horizontal asymptote of y is equal to 0. It does approach the x-axis faster than 1 over x did. If we increase the exponent on the denominator to be to the third, we still have this same behavior. It's actually just approaching the x-axis even quicker. If we change it to the fourth, we have the same thing. If we change it to the fifth, same thing. Sixth, seventh, 100th power. Oh, that is very steep in the short run, but in the long run, it gets close to the x-axis extremely quickly. This is true even if we change the numerator to a very large number. It is still approaching the x-axis as x goes to negative and positive infinity. It is also true if we have a number times something in the denominator. As long as there is an x to a power down bottom and a fixed number up top, you will always get that the function approaches 0 in the long run in both directions, positive and negative infinity. Let's look at a couple examples of how we might use this. In example 1, we have the limit as x approaches infinity of 10 over x to the fourth plus 6. Now we haven't really talked about specific rules for how do you find the limit of something when it's kind of got like two pieces to it. But what you can do is split this up into the individual limits. So we could say that this is the limit as x approaches infinity of 10 over x to the fourth plus the limit as x approaches infinity of 6. Now this function here, 10 over x to the fourth, is an example of what I'm talking about here. Fixed number up top and x to a power down in the bottom. So this whole thing is just going to be 0. Then if we look at the limit as x approaches infinity of just 6, well, if you have just a constant here, the limit is always just that number. So this is just equal to 6. We have 0 plus 6, that is just 6. And so the value of this limit here is 6. Looking at a graph of this function, we can see that it does indeed have a horizontal asymptote of y equals 6. In example 2, we have the limit as x approaches negative infinity of 5 minus 2 over x squared. Now again, we can split this up into two separate limits. We can consider the limit as x goes to negative infinity of 5 separately, and then subtract the limit as x approaches negative infinity of 2 over x squared. Now here we have a similar situation. We have the limit as x goes to negative infinity of another constant 5. No matter what x is approaching, again with a constant function here, this limit will always just be the constant. So that's just equal to 5. Then we will subtract what we get when we take the limit as x approaches negative infinity of 2 over x squared. This is another example of something that looks like this, a fixed number over x to a power. X approaching negative infinity of something like that will always also be 0. So here we've got 5 minus 0, which is of course just 5. So that's the value of that limit. Here's a graph of the function that we just found the limit of. We can see again that this has a horizontal asymptote, and it's at y is equal to 5. Of course, there are a lot more rational functions than ones that just have simply a power of x in the denominator. Right, we can have a whole polynomial in the denominator for a rational function, or even in the numerator. If we want to find the limit as x goes to positive infinity or negative infinity of any general rational function like this, where again the p of x and the q of x are polynomials, powers of x added and subtracted, maybe with numbers multiplied, then all we really need to do is consider what is the highest degree of the top and the bottom. There are three possibilities. The function could be bottom heavy, which means that the degree of p of x, the numerator, is less than the degree of q of x, the denominator. So you've got higher degree down in the bottom than up top. The second possibility is that the function is what I'd call balanced, where the degree of the numerator is equal to the degree of the denominator. Then the third and last possibility is what I'll call top-heavy. This is where the degree in the numerator is larger than the degree in the denominator. It's important to note that what we mean by degree of the numerator and the denominator, this is referring to the largest power that occurs in the top and bottom. When we talk about the degree of a polynomial in general, it always refers to the largest power that appears in that polynomial. Depending on the degrees, we get different horizontal asymptote situations. If the function is bottom heavy, then as x approaches infinity or negative infinity, the denominator will get a lot larger than the numerator. That will drag the whole fraction down to become very small. So in this case, we have a horizontal asymptote of y equals 0. And this is true in both directions, meaning as x approaches infinity or negative infinity, we will have a limit of 0. Here's an example of a function that's bottom heavy. We have a squared degree in the top as the largest power, and in the denominator, we have a third degree that is the largest power. So when we plug in really large x values, the denominator is going to get much larger than the numerator, and so this will have a horizontal asymptote of y is equal to 0. In the second possibility, when the degree of the top and bottom are equal to each other, the horizontal asymptote is going to be the ratio of the coefficients. So I write that as y equals a over b, and this is again in both directions, positive and negative infinity. And the a and the b are the leading coefficients of the polynomial in the top and in the bottom. So a is the leading coefficient of p of x, and b is the leading coefficient of q of x. The leading coefficient is the number that is multiplied by the largest power of x. For example, if we have the function f of x equals negative 2x cubed plus 3 divided by 3x cubed plus 1, very similar to the previous example, but here we have the same highest degree in the top and in the bottom. So the horizontal asymptote is going to be the ratio of the leading coefficients, which are negative 2 in the top and 3 in the bottom. So our horizontal asymptote will be y equals negative 2/3. In the third situation, where the function is top-heavy, this will have no horizontal asymptote. If the degree in the numerator is greater than that in the denominator, this makes the whole function get very large if you plug in very large x values. For example, if we have the function f of x equals negative 2x to the fourth plus 3 divided by 3x to the third plus 1, here we see that the degree up top is 4 and the degree in the bottom is 3. So this is what we would call top-heavy because of the relationship of the degrees. And this function will have no horizontal asymptotes. Based on what we just talked about, pause this video and see if you can match the function with its graph by analyzing the horizontal asymptotes. Since the first function is bottom heavy, it will have a horizontal asymptote of y equals 0. That matches with the graph labeled C. The second function is balanced. We have degree of 2 up top and degree in the bottom. So that means that the horizontal asymptote will be the ratio of the leading coefficients, which will be y equals negative 2 over 3. That matches with the graph labeled A. The third function is top-heavy. The degree up top is larger than the degree in the bottom. That means that the graph of this function will have no horizontal asymptotes. The graph labeled B has no horizontal asymptotes because it just increases as x goes to negative infinity and decreases as x goes to positive infinity.